We're going to talk about vibration fatigue. Vibration fatigue is our marketing name for doing fatigue in the frequency domain. So most of the things we've seen today, we've brought in time histories or time elements and basically rainflow counted the time signals. Here we're talking about looking at a frequency-based input, either swept-sine or a PSD input. We do that for a couple reasons. Certain structures are very well defined using that style of acquisition. Not so really practical in Detroit, but if you go off and look at like offshore structures or wind turbines, they need to have a dynamic analysis, but they also need to have a very, very long duration acquisition, maybe months or years. And there's no way to have years of time history, realistically. So it's real advantageous to look at it in terms of PSD. Here in Detroit, we see this a lot in terms of components that we're going to basically we're going to qualify with some sort of electrodynamic shaker table input via PSD. And things like that are things like going off the engine, components off the engine, fuel rails, you know, some sort of assemblies off of brackets. So those are applications where we'll see this. And basically what we're going to do, we're going to use the same sort of approach that we use time-based, but now our FE input, instead of being either modal transient or being static, is going to be some sort of frequency response. And that's got different names depending which analysis code you're using, is Solution 111 or a steady state dynamics, harmonic. But it's going to look at a frequency response. We'll pair that up with an input PSD. And then inside of DesignLife, we'll generate PSDs of stress inside of DesignLife to do the fatigue prediction. And there's like little magic boxes that can look at these PSDs of stress and calculate cycles. We've actually had this for a while. Some additions that were in DesignLife that weren't in FE fatigue previously. One is the ability to go off and bring in static states to add mean stress to these calculations. And so the actual calculation itself has a zero mean. And if you have residual stresses caused by some assembly configuration, you can go in and basically bring in a static analysis that would have that, and we'd add it to it, do the mean stress correction. The other thing we have here is the ability to actually bundle this into a duty cycle. And most people have test rigs that are single axis, but they do 3-axis testing sequentially. So you go off and actually test a part in the X, stop, put it on its side, test it in the Y, stop, test it in the Z. And we can actually do that very easily with a duty cycle. I'll show you. Okay, so we're looking at the basic process, same sort of process we use anywhere else. Here, though, we have slightly different inputs. And if I were to look at the DesignLife process or flow, it looks very, very similar to what we've seen today. One big difference is that the input for the finite element portion, the geometry or the finite, is going to be coming in from Nastran or Abacus or ANSYS, but it's going to be what we call an FRF. It is the output of this steady state dynamics or frequency response. And what it really is, it's a frequency sweep across a range of frequencies we're interested in, and we're saving out the complex stresses, the real and imaginary stresses for those. And that's relatively new to DesignLife, but the reason we do that, it gives us an ability to calculate principal stresses or directional stresses from these. So again, the solution that you're going to be doing is some sort of harmonic analysis. That harmonic analysis, no matter what analysis code you're using, you're going to put a unit sweep across the frequency range. And this unit load could be acceleration, it could be force, it could be displacement. One thing we have to do is we have to worry about units in general. And we want the units of this harmonic to actually match the units of the PSD. And what that really means here is that if my PSD is going to be x squared per hertz, I want my unit excitation to be an x. Okay, so if my PSD is in g squared per hertz, it's acceleration, my input's going to be 1G excitation. If my PSD's in Newton squared per hertz, it's going to be basically inputs of newtons. Again, we're going to save complex stresses, and currently we're bringing in stresses at a range of frequencies specified by the user. Each one of these is going to be a snapshot of the response at that particular frequency. These can get very, very large. If I have a very large frequency range and I want a high resolution in terms, I want a very short, small increment in terms of frequency, you can end up with very, very large files. One of my recommendations is try to save the results out clustered rather than just equal increments. And so you can go off and do that depending on the analysis code you're using. But like I said, for Nastran, I'd rather to use like a freak 4 rather than a freak 1 to try to save the results out. Clustering means I'm pushing all these frequencies around the modes of excitation. And that's typically what I'm interested in anyhow. The other issue, obviously, this is dynamics. We're interested, because we're working in the frequency domain, we're interested in dynamics, which means I'm looking at a trim model, which, some of us that we don't really care because the whole mass for our part is basically just the part's mass. Other of us have parts that, maybe only a tenth of the mass belongs to the part, and everything else are, masses attached to it. And we have to look at that whole trimmed assembly. Secondly, we need damping. And that actually came up earlier in conversations, that the one thing that makes fatigue look like an exact science is damping. And so that we need to worry about damping in the system. We're going to put the damping in the FE analysis, but that eventually comes downstream to DesignLife in terms of what the excitations look like. So this is our FE input. We have a second input we need to bring in, and that is the actual excitation we're going to be applying to the structure in the test. This can be either PSD or swept-sine. And one of the things that we see here is that there's a variety of ways to get this into into DesignLife. There's actually 3 different inputs, multi-column, histogram, or actually time series as well. And the same information going in is just different file formats. So if I'm looking at the multi-column, we're looking at something like a CSV file or Excel spreadsheet. If I'm looking at the histogram input, we're actually looking at a PSD generated from either a vibration generator, possibly using ASCII translate to do the calculation. One big difference between these, which actually becomes important later on, if I brought in an Excel spreadsheet, I bring in frequencies that I actually specified. So if I put in 5 frequencies with their excitations, I'd only see those 5 frequencies come into DesignLife. If I'm coming in with this file format, the PSD, the histogram file format, what that actually is a starting frequency and an increment. So I might actually, inside the generator, put in 5 frequencies, 10, 50, 100, 1,000. But what this is going to spit out could be hundreds or thousands of steps. It's going to basically be, if I told it that I wanted to have a starting frequency of 10, an increment of 10, and I'm going to 1,000, I'm seeing 100 steps inside there, even though I only put in 5 increments. Okay? This becomes issue later on because we're going to actually tell the software where to do the analysis. And one of the things we can tell it is, I want you to use the frequency steps coming in as analysis points. Well, I put in 5 locations here, I get 5 analysis points. I put in 5 locations here, but it spits 100 into DesignLife. We do the calculation 100 times. Okay. And I just threw this out here in terms of consistency, but the idea is that if I'm going to have an input coming in from that PSD or that Excel spreadsheet that's in like G squared per hertz, then I want my analysis inside of FE to be basically in terms of Gs. So it'd be whatever unit system I'm in, but basically I have a 1G excitation. And again, the same sort of thing whether I'm working with force or displacement. So those go into DesignLife, and then like any other analysis, we have a load provider. And the load provider for vibration, basically we have an upper entry that just points to the the harmonic analysis or the steady state dynamics analysis that we're bringing in. So we bring that in. Down below, we have available any of the PSDs or swept-sine signals that were specified, and we basically just pair these two up. And then in the center, we have the ability to point to an additional FE input that would be the static stresses. So that all looks pretty straightforward, but there's another button up here. And the only way you can get to this button is to be in advanced edit. So you have, in this particular load provider, even though you can see the load provider, this portion of the load provider on the outside, you want to go into advanced edit. I rarely say that. So if I go in and pick that second tab, we see this. And so these are properties that are actually controlling the vibration load provider. And the first top portion here is consistent between both PSD and swept-sine. And here's a setting that specifies at what frequency breakpoints do I solve things at. And we have basically a couple of options. I can use the frequencies coming in from the PSD. That's what loading means. And here's where that big difference comes in between bringing it histogram or Excel. You know, it's whether I'm doing 5 calculations or 100. Okay. The second entry here, FRF frequency, means the frequency steps that were saved out of FE. And so these would be all the frequencies that came in from Nastran or came in from Abacus or ANSYS. And the options up here are basically, I can do the loading, I can do the, basically what comes in as a PSD, I can do what comes in from the FE, or I can do the combination of the two. And generally, the combination of the two is probably the safest solution. And then there's one additional solution that says it's user input, where you can go in and say, I want to go from this frequency to that frequency by that interval. So I could actually just pick a range. When we are looking at these PSDs coming in or swept-sine, we have the option of how we actually interpolate from one step to the next. And so this right here basically says the interpolation log-log, linear-linear. If I'm bringing stuff in from a histogram where I have a very fine resolution of frequency, this doesn't have much of effect because I've got a very small increment from frequency to frequency. If I'm bringing stuff in from the Excel spreadsheet where I have big jumps, 10 hertz to 100 hertz, 100 hertz to 1,000 hertz, this has a huge impact. Okay. Number of bins. We're going to take what comes out of DesignLife, which is going to PSD a stress, and we're going to count that. And we're going to put it into basically a histogram, a 1D matrix. And this is how many bins are in that matrix. It's my personal opinion that you want this much higher than 64. I'd put that to like 1024, so you have a fairly fine resolution. The only downside to this, there's one counting method in PSD, it's called LAN, that actually slows down as this thing gets bigger. But I'd still take the hit and set it up to either 512 or 1024. It doesn't even have to be a power of 2. Okay, and then finally, we specify what's coming in, a swept-sine or a PSD. If we call this a PSD, we actually have 2 more inputs. They show up down here. One is a counting method, and I'll show you that in just a second. And the second is exposure duration. Here. Okay, so I should have just said this already. 1, you need to be in advanced edit. 2, the FRF loading ranges basically specifies where we're going to solve things. One difference between us and like Nastran is if the ranges of the FE results and the PSD don't match, DesignLife will take whatever one stops first and just continue that value on. It doesn't drop to 0. It gets continued on. And so if you want the PSD to actually drop to 0, you want to really specify the last range as 0. Interpolation method is important for multi-column. Again, I said that. Bin count, I would have the bin count much higher, and there's a hit. Exposure duration is, back here for 1 second. This exposure duration actually is dealing with the fact that PSDs have no relationship to the actual time element of the time history that created them. I might have a time history that was 10 minutes long. I turn it into a PSD, it's lost that information. So we actually have to tell DesignLife how long we run this PSD for. And so this guy here is basically how long the increment is we're going to run the PSD, and then we'll get answers out in that increment. That thing's in seconds. And so basically, if I set it to 1, my life will come out in seconds. If I set that to 3,600, my life would come out in hours. Okay. And then the counting method that's there, you've got 4 options. It's narrowband, Steinberg, Derlich, and Lalande. Basically, narrowband was the original technique. However, it only expects to see 1 frequency content, multiple frequency contents within the signal, and this becomes very, very conservative. Not unconservative. Steinberg is an empirical technique really geared towards electronics. We've included it because still there's electronics qualified that way. The 2 general purpose techniques are Derlich and Lalande. They both have reasonable performance, and what these actually do is they take the PSD of stress and basically come out of it with some sort of estimated, think of this as a histogram of cycles. And so they've just assumed the shape of the histogram. What that actually means, I'm a civil engineer, so I've never really dealt a lot with like imaginary numbers, and so I didn't really trust some of this here. So what I actually did at one point was I created a time-based solution above where I actually have time histories coming in, modal superposition, and down below I had exactly the same inputs but via PSD coming into Lalande, Derlich, narrowband, and Steinberg. And the target up here, I believe that one because it was in the time domain, it came up to be 16,000 minutes. And so I ran the other techniques against it, and you'll see that both Lalande and Derlich come reasonably close to the time-based method. Narrowband, I said, is going to be over-conservative if there's a mixture of frequency, if there's multi-band, a wideband frequency content, and so it's relatively conservative. And the scary part is Steinberg. It didn't see any damage whatsoever. So you'll see people, you actually use Steinberg because you almost do Steinberg by hand. But there may be issues there. Okay. The top portion is the same here, but here we've set the loading method. Instead of PSD, we've set swept-sine. And I just wanted to point to, when we do that, there is 3 parameters we can set, and that's how quickly we sweep through that range. And I'll show you something in just a second. It's the actual rate we're sweeping through with this sweep type, and then how many sweeps we're making. And so basically, if I know the frequency range I'm going through, and I know the rate and how basically what that rate really means, I can tell you what the duration is. And so the three sweep types are just linear hertz per second, which I could actually figure out myself. Log seconds per decade and log octaves per minute. And there I actually had to go off and do Wikipedia. And it took me about a morning to figure out the sweep rate, what they meant versus duration. But I actually have these as equations so you can figure out what these are. These are actually, if you have someone who's actually using the electrodynamic shaker table, they understand this. This is what they're actually putting in. And so we just mimicked what that was. So those are just, so you can work out duration versus sweep rate. Okay. And finally, coming out of this, you get life. But they always get a question, well, what does this actually mean? So if we're looking at swept-sine, we're actually looking at the number, we get life out, and life was 5. It'd be 5 times through the sweep, or 5 times through the sweep that was specified. Again, we specify a range of frequency, a sweep rate, and how many sweeps. So you'd have 5 times that combination. If you have a PSD input, we brought in something called exposure duration, how many seconds we're actually running. And so life comes out in repeats of exposure duration, Remember I said if you left it at the default of 1, life would be in seconds of operation. If you set it up to be 60, life would be in minutes. So you're getting repeats of whatever the exposure duration is. And then again, we can do duty cycles, and when you get life out in terms of a duty cycle, it is just repeats of whatever the schedule we specified in. Do they stay on here? No, they don't. Okay. If you look at results coming out of these, and this happens to be PSD results, there's a couple things that come out. One is life, and again, life is repeats of whatever input we're bringing. Exposure duration, sweeps. There is another output here that's of interest. One of the benefits of this approach is I called the cycles coming out a histogram, and that was really a lie. What that really is a probability density function. And what that means to us is that even though it looked like it went to 0, it never goes to 0 in terms of number of cycles. As you go out in larger ranges, it continues to have a tail going out with a certain percentage of cycle. And if I were to ask it to run long enough in time, eventually you'd hit those very, very large stresses. This is actually a input here. They'll come and tell me if I specify exposure duration, what's the largest stress it would expect to see in that exposure duration. So if I ran this for a second, I'd get 1 stress. If I told it to run it for a year, I'd get a much larger stress because there'd be an infrequent load go in it might see. That combination doesn't really impact life. Life is purely exposure duration. In terms of exposure duration, so if I had exposure duration of 1, a life of 1,000. If I said exposure duration of 1,000, I get a life of 1. So it's purely Miner's rule. Here, this is the one column that you'd see the big difference. Where if I go in and I increase the exposure duration, I'll see larger and larger possible stress cycles. There's another one here that's useful as well, and that is the same information just in a different way, and that is, again, how long it takes to hit UTS. Remember, I have this probability density function that if I run long enough, I'm eventually going to hit a big cycle. Okay, and so this is how long do I have to run in seconds before I hit UTS. This is really useful in letting you make a decision of whether I'm looking at static failure or I'm looking at fatigue. Again, if I run and I'm hitting UTS in a matter of seconds or even minutes, I'm really looking at bumping it against static failure. If this is a very large number, then obviously I'm looking at fatigue damage. Okay. This actually, again, is very easy to program in terms of duty cycles. And so I could set up an analysis where I have not one vibration fatigue analysis, but I have 3 in a duty cycle. 3 different PSDs coming in, 3 different harmonic analyses coming in, 1 in the X, 1 in the Y, 1 in the Z. And I can very easily program this to make it look just like the shaker table test that I would do for 3 axis. Okay? Questions?